In this lesson, we'll look at the different types of formulas that are useful to chemists, and we'll learn how to take certain types of data in order to help us to determine what is called the empirical formula. Many chemists spend a lot of their time trying to synthesize or make compounds in the lab. A lot of the compounds that are synthesized are ones that are found in nature. So, for example, vitamin C or vanillin, which is the component of vanilla that gives vanilla its flavor. These are synthesized in the lab, but in order for us to synthesize them in the lab, we need to first know what their structure is. Ultimately, to determine what something's structure is, we want to determine the arrangement of the atoms in that particular compound. But it would be very difficult for us to come up with a structure without first knowing what the formula of a compound is. There are different techniques that we can use in order to help us to determine what is called the empirical formula. The empirical formula is a formula that shows us the simplest ratio of the atoms in a formula. All ionic compounds have empirical formulas because, as you know, they're listed with their simplest ratio. But as you know from organic chemistry or for dealing with any molecules, we don't simplify the formulas. So it is possible to come up with an empirical formula of that, which is its simplest ratio. The molecular formula is the formula that you're most used to using, and that's the one that shows the exact number of atoms that are in a particular compound. As you know from organic chemistry, we can draw structures of compounds, and the structural formula shows the arrangement of the atoms. So ultimately, we want the structural formula. To be able to come up with the structural formula, as I said, we need to know the molecular formula. And the molecular formula will be determined from knowing what the simplest ratio is, or the empirical formula, and knowing what the molar mass of a particular compound is. So chemists have different techniques for determining each of these formulas. And when we take all of the techniques and apply them together to one unknown compound, we're able to predict or understand what the structure of a compound is. What we're going to look at now is how we can determine the empirical formula of a compound. The method that we're going to use in this lesson is to use mass data from experiments or a percentage composition as the same type of percentage composition that we were working with in the last lesson. We're going to take this information and determine the formula. Let's look at the examples. In the first example, we have an experiment where 2.52 grams of hydrogen is reacted with oxygen to produce 22.5 grams of a new substance. We want to use this information to find the empirical formula of the new compound. So I'm going to look at what we have here. We're reacting hydrogen and we're reacting oxygen, and we're making some unknown compound with hydrogen and oxygen. Now we can't automatically look at this and assume that it's going to be water, because there might also be other possible ratios of hydrogen and water combining. So in this case, we had 2.52 grams of hydrogen reacting. And we know that our final product had a final mass of 22.5. Using the law of conservation of mass, we're able to see that the amount of oxygen that combined with the hydrogen was 19.98 grams. So I did that by subtracting 2.52 from 22.5. Now this mass data alone is not going to be helpful to me, or it might be a little bit more complicated than what we want to do at this stage. So what we're going to do is take the data that we have and find the percentage composition. from the percentage composition, we're going to determine the empirical formula. So let's find the percentage composition. We want to find the percent of hydrogen in this unknown and the percent of oxygen in this unknown. As you know, in the sample, out of the 22.5 grams, 2.52 of it is hydrogen. So we can determine what that is as a percentage. So 2.52 divided by 22.5 times 100. We find that that gives us a percentage of 11.2. For the oxygen, out of the 22.5 grams, 19.98 of it is oxygen. So we can find what that is as a percentage, which is 88.8. Now again, we could have taken 100 and subtracted 11.2 to get the 88.8, but I like to verify that I've done all my initial calculations correctly. So we know that in this unknown sample, it is 11.2% by mass in hydrogen and 88.8% by mass in oxygen. So what we have right now is a ratio of hydrogen to oxygen in the sample. But in looking at a formula, the formula is telling us the ratio of the actual atoms. So when we look at a formula, we are counting the number of hydrogens compared to the number of oxygens in the sample. So this ratio is not in grams. It is in numbers of atoms. So we're going to need to use this mass and be able to change this ratio so that it's with respect to the number of atoms of hydrogen compared to the number of atoms of oxygen. Now, to deal with the actual number of atoms, we could do that, but we would be dealing with really large numbers, and that's why we have the mole. So not only is this an atom ratio, it's also the mole ratio. So for every X number of moles of hydrogen, we have Y moles of oxygen. Just like for every 1 hydrogen, we have 1 oxygen. So let's use that information and determine the empirical formula. I like to organize my data in a chart for empirical formulas, because sometimes you end up with a formula that has 4 or maybe even 5 elements in it, and when we're analyzing the ratios, it can get a little bit messy. So if we use a chart, it's going to be helpful. Okay, the headings of my chart are the element, the mass, the moles, and the ratio. So the elements that I've got in my sample are hydrogen and oxygen. Now I have a percentage by mass. So I want to turn that into a mass. And so what I'm doing when I determine empirical formulas from percentage compositions, I'm going to work with 100 grams because that is the simplest number of grams to work with. If I work with 100 grams, then if I have a 100 gram sample, I know that I have 11.2 grams of hydrogen and 88.8 grams of oxygen. So your percentages become your masses. Now we want to find out in 11.2 grams of hydrogen how many moles that is. So we use our formula. Moles is equal to the mass divided by the molar mass. Okay, now keep in mind here we're talking about just the element hydrogen, so we don't have to worry about Hofsprinkle or anything. It's going to be 11.2 divided by 1.01. We get 11.0989. Now, a big piece of advice for dealing with these charts is to carry a lot of significant digits. Okay, what you're going to find is that ultimately we're going to want whole numbers for our final answer. And if you round too early, you might end up with data that you're not really sure about and it's unclear to you how to round. The best way to deal with that is to make sure that you're carrying lots of significant digits. So for oxygen, the moles of oxygen that I have is 5.55. So I started here and I had a mass ratio of hydrogen to oxygen, and now I've narrowed it down to a mole ratio of hydrogen to oxygen. So for every 11.0989 moles of hydrogen, I have 5.55 moles of oxygen. Now, as you know from chemical formulas, we always use whole numbers because we want to see the ratio of the individual atoms to one another. So our next job here is to convert this ratio into a whole number ratio. And a technique that we use to do that is to put it into a 1 to Z ratio, 1 to something ratio. The way that we do that is by dividing both amounts of moles by the smallest amount of moles. So if I take both of these and I divide them by the smallest value here, which is 5.55, and I'm left with 1.998 for hydrogen, and then for the oxygen, 5.55 divided by 5.55 is equal to 1. And as you know, in math, if you've got a ratio and you do the same thing to both parts of the ratio, you haven't changed the ratio. You've changed the form of the ratio, but you haven't actually changed the ratio. So here, when we do this, now I can see that I've got a whole number ratio. Okay? I've showed you here, if you plug this number into your calculator, you're going to get 1.998. Okay? That you're able to round to 2. Okay? So what we have here is when we have this sample that is 11.2% in hydrogen and 88.8% in oxygen, that's the equivalent of for every 2 hydrogens, there is 1 oxygen. So therefore the formula is H2O. Okay? And it just so happens that this one was water. Let's look at another example. We've got an iron oxide, so we know it contains iron and oxygen, and it contains 69.9% iron and 30.1% oxygen. We want to determine the empirical formula. So anytime we want to determine the empirical formula, we're going to set up our chart. So we've got element, mass, moles, and ratio. And I've got my iron and my oxygen. So I'm going to work with 100 grams. The percentages become the masses that I need to deal with. To determine the moles, I divide by the individual molar masses. So for iron, I divide by 55.85, and for oxygen, I divide by 16. And the values that I get are 1.25, 1.6, and 1.88, 1, 1.25. Now again, I have a mole ratio, but I want to determine what an equivalent whole number ratio will be. So my first step is to divide by the smallest value. So I'm going to divide both of them by 1.2516. Okay, so when you divide something by itself, it becomes 1. In this case, when I make this calculation, I get a value of 1.5. So my first technique of dividing by the smallest number of moles is still not giving me a whole number ratio, which is not unusual. What we need to do is then analyze this further and decide what I need to do in order to convert this ratio, a 1 to 1.5 ratio, into a whole number ratio. And the way that we're going to do that is by multiplying by the appropriate factor. So what you need to do is take the value that's not a whole number and decide what it could be multiplied in order to make it a whole number. If I take 1.5 and I times it by 2, that's going to give me a whole number of 3. Now I can't just change this one without changing the other factor in the ratio, so I'm going to also multiply this by 2. And so I get my final ratio of iron 2 and oxygen 3. So my formula is Fe2O3. And the name of this is iron 3 oxide. Okay, so in this question, what we've essentially determined is we've got this unknown iron oxide sample, and we've determined what the charge is on the iron in that sample by determining its empirical formula. Just a little side note about this final step here. When you're deciding what you need to multiply in order to get a whole number ratio, what you want to do is, if you can't see it right away, like some of you may have seen right away, oh, I just need to multiply that by 2. If you can't see it right away, you can do trial by error. So, for example, if I had the ratio 1 to 1.25, okay? Some people are better at mental math than others, and some people will see right away what the multiplier needs to be. Others might not see it right away, and that's completely fine. You just need a strategy in order to be able to determine the correct ratio. So trial and error works great here. Okay? If I multiply by 2, that's not going to work. I'm going to get 2.5. If I multiply by 3, that's not going to work. If I multiply by 4, that's going to work. Okay? So if I multiply this by 4, I end up with 5, and this one becomes 4. So by using your calculator and doing trial and error, you can come up with the right ratio. Now, one thing to note here is that you don't want to round too much. Okay? The number that you multiply by should give you very close to a whole number. Okay? You're not going to take something like 4.8 and round it to 5. Okay? You should always be getting really nice whole numbers in these questions. And if you're not, what you want to review is the number of digits that you're keeping in your moles calculations. At this stage, there are several practice exercises, okay, both within the chapter, practice exercise 9, and several questions at the end that are listed in your notes. So you should take the time to work through each of them carefully and check your answers, asking about ones that you're having difficulty with.